So the rational root theorem gives us a way to determine if some nice rational numbers, by that I mean fractions or integers, are roots of a polynomial. And it turns out all we have to do is look at the different factors of the last term and the first term, or the last coefficient and the first coefficient. So in our particular case, with example A, we've got P is going to be factors of 6. So those are your factors of 6. Q is going to be your factors of 105. So there's a lot of those there. Now, if you take a look here and do a little bit of thinking, you can figure out how many possibilities are you going to have overall. There's 4 possibilities here. 1, 2, 3, 4, 5, 6, 7, 8 possibilities here. So 4 times 8 would be 32 possible combinations of these things. And then we got to account for the plus or minus. So overall it'd be 64. But if this graph's going to cross the x-axis at a rational root, it has to be of this form. It has to be P over Q. So to get all these P over Q possibilities, what you should do is just be methodical. Start out with P equal 1 and divide it by the various values of Q. So 1 over 1, 1 over 3, 1 over 5, all the way up to 1 over 105. And then move down to the 2. 2 over 1, 2 over 3, 2 over 5, etc. And so on. You do it all the way up to 6. Now, if you look carefully through this, you might find some things that are redundant, some things that are kind of listed twice. So can anyone see a number that's in a way listed twice? For instance, what's 3 divided by 3? 1. That one's kind of listed twice, right? What else is listed twice?
2.
Yeah, 2. 2 is 6 over 3. It's also 2. And so on. There's a lot of different places where you have multiple listings. 6/15 in lowest terms is the same as 2/5. Just divide out the 3. And so on. Now, I'm not really worried about that part of it, but this is your rational root theorem. Now let's graph this for a second on our graphing calculator. I hope that everyone's got one today. So let's clear this out. Y equals, and I want to, let's see. Yeah. Lucky day. That's the one that we want. So if you need a graphing calculator, I think you guys know the drill. Thank you. So far as my window is concerned, here's the window that I'm going to use. Now I've already kind of zoomed in a little bit for us here. So it's from -1 to 1 on the x-axis and -20 to 10 on the y-axis. And let's see here. Let's take a look at our graph. And it looks like that. Kind of hard to see where this graph crosses the x-axis, isn't it? It'd be nice if we could zoom in and see it a little bit better. So let me teach you a trick about zooming in while I let the people who are just getting their calculators catch up. If you click zoom, the first option there is zoom box. And what that lets you do is zoom into whatever part of the screen that you want. So if you click zoom box, so zoom and then press 1 or zoom and press enter, that's going to leave you with a cursor on your graph. And let's just find a place that looks like a good viewing window and then click enter once. And when you do that and start to drag, it'll open up a line. And then if I drag to the left, it opens up a box. When I click enter again, this will be my new viewing window. So I'll be effectively zooming in on the part of the graph that I actually care about. So let me press enter, and I should see a little bit better of a graph. Okay, all right. Now, the rational root theorem says if this graph crosses the x-axis at a place other than things like square root of 2 or e or pi, then it's going to do so at one of these values. Now, looking at my graph, I see something, that it crosses the x-axis a little bit to the left of negative 0.4. So I'm going to take a wild guess that maybe, I don't know, something close to negative 0.4 would be negative 3/7, is about negative 0.428. So that looks like it could be the rational root. But is it? Is it really the rational root? Well, we can find out. Hit the trace key on your calculator. It doesn't matter what the window is as long as you can see your roots here. The trace key allows you to kind of zoom around and trace, but it's a little bit more powerful when you know where you want to trace. And I want to find out what happens at the point negative 3/7. Once you've hit the trace key, if you type in a number, it'll open up a little window at the bottom, negative 3 divided by 7, and bam. Now, how can I tell that I actually hit the root there, that I hit it exactly?
Because y is 0.
Perfect, because the y coordinate is 0. Wow. Now, you can also do that with the table. If I hit second and then table, I can type in negative 3 divided by 7, and I get 0 again. Lucas?
I'm sorry, where was negative 3 over 7? Was it from this table set right here?
Yeah, so negative 3 over 7, these are the possible rational roots. If this graph crosses the x-axis at a rational root, it's going to be one of these, either plus or minus all these.
I see.
So, yeah, there's a plus or minus that's out in
I
front.
didn't see that.
And bam, we got one of our roots. Let's take a look at another one. 0.4, does anyone know what the fraction is for 0.4? That'd be 2/5. Good. So 2/5, let's see, do I have a 2/5 in here someplace?
It's green.
Yeah, there it is. So there's our 2/5. You can type in 2/5 or 0.4. That gives you another root. So this is a nice way to verify that you've actually got the right roots when you're working with your functions. You can check it on your graphing calculator. Now, the point of this first problem was just to try and figure out what are the possible rational roots. When I give this problem on an exam, I'm going to make the set of numbers smaller so you don't have to go through 32 of these possibilities. But are we okay with these? And we could take a guess at, that third root, but I want to move on. Comments or thoughts on example A? Yes?
So when you plug in 2/5, just because so the answer as a root would be not 2/5, it'd be 0.4.
Well, 2/5 is 0.4, so those are the same thing.
Yeah, crazy.
That's all right. No, that's all right. I appreciate you thinking through this. Let's move on to example B. And it says, list all the possible rational zeros. We're going to go a little bit farther than that on this one. Well, actually, no. I'll hold off on that part for a little bit. Question? Angel, can I help out?
Because I'm trying to get the graph and I can't get a good window set.
So let me just back up and show you the window setting that I have currently. So you can go -1 to 0.5 would probably be a good one. And then -10 to 4. It doesn't have to be all these decimal values. That came about because I chose, those numbers by happenstance when I did my Zoom box. All right, let's move on to example B. I've got r of x is 2x to the 5th plus, 9x cubed plus 6x squared minus 6. So let's just zoom in a little bit there. It's a little bit easier to read now. So the numbers you want to focus in on are these numbers. And I need to come up with two things. P is going to be the factors of which number? Of 6. Good, so P is going to be the factors of 6. And Q is going to be the factors of 2. Now, fortunately and mercifully, these numbers are a much smaller group than our previous set. Factors of 2. Now, the factors of 6, the things that go into 6 are 1, 2, 3, and 6. 6 is a perfect number.
Wait, what is Q is the factors of 2? Is that what you said?
Yes, Q is the factors of 2, and P is the factors of 6. So, Sabira, what numbers go into 2 evenly?
1 and 2.
1 and 2. Perfect. Now, overall, I've got 4 numbers here and 2 numbers here. 4 times 2 is 8. I could expect up to 8 different combinations of P over Q, but I'm thinking that a couple of these are going to be redundant. So there's a couple of these are going to be repeated. So let's do plus or minus P over Q, which is going to be plus or minus, and let's just start listing these things. Work methodically, work in order. Start with P equals 1. 1 over 1 is 1, and then 1 over 2. 2 over 1 is 2. Do I need to list 2 over 2?
No,
Why not?
because 2 over 2 is 1.
Exactly, 2 over 2 is 1, so I'll skip that. Then I'll move on to 3. I've got 3 over 1 and 3 over 2. What's the last unique number that I need to list? 6 over 1 is 6. Do I need to list 6 over 2?
No.
No, because that's kind of already there. We've already got a 3. So plus and minus these, those are all your numbers. Now, just kind of a heads up, I don't know what WebAssign is going to want. I don't know as though they do the plus or minus here for you like I do. So WebAssign might want you to list them all out. So you could list them all out this way. It'd be -6, -3, -3 halves, -2, -1, -1 half, and then 1 half, 1, 2, actually 3 halves, 2, 3, and then 6. So you might have to list them all out as opposed to getting away with just doing the plus or minus. The plus or minus is fine for me on a test, but please don't forget the plus or minus out in front of the curly braces, that set notation. So that's it. Those are the possible rational roots for this function. Let's kind of compare that to its graph. I'll give you another few seconds to copy that down. And like I said, you don't have to write it like this. Write it like this. I do appreciate students who from time to time put them in increasing order like I did. That's really nice, but it's not necessary. So if you follow along the Desmos link to this page, let's see.
Quick question.
Yeah, go ahead.
What was the difference between where you wrote it up top versus the bottom?
So the way I wrote it up top, I just put the plus or minus out here, meaning it's up to the reader to realize that there could be plus or minus 1, plus or minus 1 half, plus or minus 2, etc. Here I just listed them all out. So I've got 1 and -1, 1 half and -1 half, etc. So it's just a difference in style.
Okay. Either way is fine.
Either way is fine. That's why I've got the or here.
Okay.
Yep. Let me find the link here. It should be this one. All right, so here's example B. And well, it looks like there's only one root here for this polynomial, 0.685. Does 0.685 look like any of these?
No.
No. So what that's saying is that the root at that point is not a rational root. It would have to be one of these if it was a rational root. It's not. That's okay. The only thing that we really had to do in this problem was figure out what are the possible rational roots, not exactly what it is. So, by the way, there's a nice correspondence between roots and factors, or roots and the degree. This is a degree 5 polynomial. Overall, that means there's 5 roots. 5 places where it touches the x-axis if you count multiplicities and complex numbers. I only see 1. So that means the other 4 are complex, and we'll worry about that in section 3.5.
How did you find that root again?
Oh, I didn't. Decimals did it for me. So you just click on it. It's kind of nice. Decimals will tell you, where some of these important points are. So unfortunately, your graphing calculator won't. Your graphing calculator, you have to go to that menu and let's see, second calc, and then you try and find the zeros from that menu that way. Second calc, and then you go for the zeros. Let's expand our work a little bit. Let's move into example C. And this one's going to be a little bit easier. It says all the real zeros, find the real zeros. All the zeros are integers, so that's going to be kind of nice. Let's set up our P is factors of something, and Q is factors of something else. Hannah, what's P a factor of?
The x, which would just be 1. No, sorry, 14.
All right, good. P is a factor of 14. And what are the factors of 14? 1.
1, 7, or 2, 7, 14.
Perfect. Johan, Q is a factor of what?
1.
Yeah. It's not really written, but it's understood that there's a 1 there. And not much that goes into 1. So that makes our life pretty easy. We got 4 times 1. There should be 4 combinations before we account for the plus or minus. So our possible rational roots are at these points. P over Q, or plus or minus P over Q, is plus or minus 1, 2, 7, and 14. Okay, great. So we get that pretty much for free. Now, a lot of the stuff that I used to teach in this course just isn't really worth it anymore because we've got so much technology. Now, you could do exactly the same thing on a graphing calculator that I'm going to do here with Desmos. And that is, we can graph this, and we just kind of look and see where this graph crosses the x-axis. So let me find a couple of these values. There you go. Now, let's kind of use our rational root theorem at least a little bit. This isn't a very precise looking graph, but if you had to guess, and the problem did promise that your zeros are going to be integers, which of these look promising? What integer values do you see that look promising when you look at the graph here for your roots? Where is this going to cross the x-axis? Well, one of them is going to be here, one is going to be here. Estimate.
1 and 2.
Yeah, 1 and 2. So there's 1, there's 2. How about this other one?
7.
Yeah, -7. Now, they asked us to factor these things. A lot of times you're not going to be able to do this, but if you can figure out the roots, then that makes your factoring job a lot easier. So let's do this. Roots, and then factor. If I have a root at x equal 1, that means I have a factor at x minus 1. Where's another one of my roots? I have a root at x equal 2. What's the corresponding factor there?
X minus 2.
X minus 2. Basically, you're moving this to the other side. And when that happens, it changes signs. The last one was -7. What factor goes along with that?
X plus 7.
X plus 7. So, wow. It asks us to factor this. So write the polynomial in factored form. So that's this part down here. Well, let's do that right here. And note to self, I gotta pick up a new pink marker. So the factored form of that is gonna be P of X equals X minus 1 times X minus 2 times X plus 7. Beautiful. And you know that you got this right because you can see that this has roots at 1, 2, and -7. Nice. Oz? Oh. Got it. Ha. Thank you. All right. Comments or thoughts on that one?
How did you get the roots again?
How did I get which one?
The 1, 2, and -7?
Oh, just by looking at the graph. So we looked at the graph and saw that the graph crossed the x-axis at 2, 0, 1, 0, and -7, 0. So that's where we got the roots.
Oh, I forgot because the roots are in the x.
Yep, the roots are your x-intercepts. Remember, there's 3 different types of vocabulary I can have for this. I can call them x-intercepts, I can call them zeros, or I can call them roots. I use them interchangeably and unconsciously, so hopefully you get used to that. Let's move on.
I have a question.
Yeah, please,
For last
Lucas.
question, we had one root, right? In B, example B.
Yeah, we only had one root there that we could see, and it was a real root. The remaining 4 roots, because it's a degree 5 polynomial, the remaining 4 roots have to be imaginary, complex.
So the answer to that in like this example C, we did P of X equals X minus 1 times X times X plus 2.
Oh, well, x
P
equal,
of X times X plus whatever, 6.8 or minus.
yeah, you know, if you did this one, if you wanted to factor it, you'd have a factor of x minus 0.685 something,
So
you know.
you only want a factored answer when there's more than one root?
I'd want a factored answer if it actually factors into something that we can get our hands on. You need a little bit more mathematical tools than we have right now to figure out the roots of this. Yeah, so that wouldn't be a test question, but example D could be. So let's flip things over and look at example D. Let's see. So example D looks something like this. Let's start out by applying the rational root theorem to this example. And let's see. So let me move over to here like this. Example D. So I want P of X equals 3x. Let's see, that's cubed. I think I got that right. Yep. 3x cubed plus 5x squared minus 5x minus 7. I want to find the rational roots of this polynomial. So, okay. Let's play our same game as before. P is going to be factors of something. Q is going to be factors of something else. Let's see what those factors are going to be. Do it like these. Okay, so P is going to be a factor of 7. Q is going to be a factor of 3. I'm not worried about the minus here because it'll all come out in the wash when I start looking at plus or minus possibilities. So Oz, what are the factors of 7? What numbers go into 7 evenly?
1.
1 and 7. And then likewise down here, 1 and 3. Thank you. When I look at all my different ratios, P over Q, how many ratios do you think I'll end up making? 4. 2 times 2. So total of 4. So my plus or minus P over Q, we'll put these together. Plus or minus P over Q, I would list it out this way, plus or minus 1 over 1, 1 over 3, 7 over 1, and 7 over 3. So there's all 4 of my possible roots, and then you add in the plus or minus, you get 8 possible roots.
For the test, could we just put like 7 over 1?
You can write 7 over 1. I mean, on the answer key, I'll write 7, but if you wrote 7 over 1, I'm not going to mark you off.
Okay.
Hannah?
So you said, and whenever we have those and it'll have like a negative 7, you just still write the positive, no matter what. And that's a pass.
So another way to write this, if I wanted to, I could do plus or minus 1, plus or minus 1/3, plus or minus 7, plus or minus 7/3. Or you could actually all list them all out. But what I mean by that plus or minus is that it could be a positive one or it could be a negative one.
Oh.
Positive 1/3 or a negative 1/3. So that's what I mean by that plus and minus out in front. So this is yet a third possibility in terms of the way you write this. Let's see if we can't figure out what a couple of these are. So let's see, we got example D. 1.23, does that look like it could be one of these values here? Not looking so good there. Let's try a different one. -1, all right, that's a good one. And this one, that looks pretty crazy as well. So of the possible rational roots, we only got lucky with one of them, right? We got lucky with -1. So let's take a look at the cool thing that synthetic division could do for us in this case. Now, our goal is to eventually write this in factored form. That's going to mean we're going to have to find all the roots. So let's see. If x equals -1 is a root, then what is a factor? Thank you, Angel. X plus 1 is a factor. So if x plus 1 is a factor, I'm going to divide p of x by x plus 1. So divide. I want to do p of x divided by x plus 1. And let's see what happens. So if I divide by x plus 1, let's do this synthetically. So the numbers I need to put here would be what? What do I need to put underneath this division sign?
The 3q plus 5x squared by.
3, 5, -5.
3, 5, -5, -7. Now, leave yourself some space here. You want to be able to write a line. I'm going to do 2 more things here. I'm going to write a vertical bar down there. What's that vertical bar for? That's for our remainder. What number should I put right underneath the 3?
0.
0. Whatever this first number is, there's always going to be a 0 underneath it. And in recent years, I've taken to the habit of writing that number there for students because a lot of people want to put something there other than a 0. So let's just start out by putting a 0 there. What number goes out in front here?
1. -1.
-1. Good. -1. And if you remember, there was 2 steps in this process. You would add to go down, and then multiply to go up. So add to go down, multiply to go up, and you're multiplying by that number out in front. If this is a root and if this is a factor, what should my remainder be? 0. So let's add to go down. That's a 3. Multiply to go up. It's going to be a -3. All right, so -3. Add to go down. Or then
2.
2. Multiply to go up, or then
-2.
Oh, wait.
-2. Add to go down. -7. Multiply to go up.
7.
+7.
Just a 7.
And what's our last thing here? Yay! A big goose egg, right? Got a 0 there. That's what we expected. Hannah?
Well, you only knew it was 0 because you're just dividing by -1, right? Or how'd you?
Well, we knew because of the graph that -1 was a root. And if -1 is a root, that corresponds to x plus 1 being a factor, meaning this will go in evenly. So it goes in evenly when I have a remainder of 0. Those things go hand in hand. If this goes in evenly, then what this is saying, in fact, let me show you what that's saying. Can you interpret this polynomial? What does that mean here for us?
Isn't it the, everybody, isn't it like the,
It's 3x squared
Three x squared
plus 2x minus 7.
Are you okay with that?
yeah, I get it, guys.
So what that's doing, I took p of x and I divided by x plus 1 and I got 3x squared plus 2x minus 7. Or, how about this? What if I multiplied both sides of this by x plus 1? If I multiply by x plus 1, then on the left-hand side, the x plus 1 is going to cancel, right?
Yeah.
That'll leave me p of x. And on the right-hand side, I'm not going to distribute. I'm just going to be a little bit more efficient. I'm just going to leave it as 3x squared plus 2x minus 7 times x plus 1. Now I can see that if I'm setting this equal to 0, that, oh, x equals -1 is one of my factors, right? Or one of my roots. So that's where you get that nice correspondence between roots and factors. So x plus 1 as a factor means x equals -1 is a root.
Oh, I see, okay.
That still leaves us with a little bit of a problem. I need to know where this could equal 0, right? Because I want to know where this times this is 0. This is 0 is fine, but where is 3x squared plus 2x minus 7 equals 0? How am I going to figure that out? I don't think you'd like to factor that one. That one would be pretty ugly. Yeah, it's going to come back to torment you. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now, I just saw somebody in my morning class writing this as if it's just the stuff under the radical that's divided by our 2a. It's everything. And please be careful with that. That will make a difference. Let's throw in our coefficients, a, b, and c. So a, in this case, would be what? 3. And b would be 2. And c, -7. Personally, my bias, because I teach this stuff, when I do the quadratic formula, I like to write a bunch of empty parentheses and then fill them in. Mostly because a lot of people make mistakes, especially if you have a negative value for b. So filling that in, I get the negative of 2 plus or minus 2 squared minus 4 times 3 times c, which is -7. Poor c only gets represented once in this formula. That's okay. And let's grind this out. That's -2 plus or minus the square root of 4 plus, that'd be 84, divided by 6, which is -2 plus or minus the square root of 88 over 6. And I hate to be the bearer of bad news, but we still got more work to do. Yeah. I feel you. Run out of paper too. In fact, I've got like just a couple pieces of paper left, so we might have to end in class earlier today. All right, I'm kidding you on that one.
Wow.
I know. Yeah, Kyle's eyes got really wide. He's like, oh man, don't do that to me. It was so wicked. Yes, sir.
Just a little bit perhaps.
Sure.
I got the rest of it.
So I'll help out a little bit. 4 goes into 88 22 times. And I'll trust that you can do the square root of 4. Now there's one last little thing that I would like from you in this one. And you can do it a couple of ways. Personally, I like factoring out the GCF of the numerator, which is a 2. If I factor out a 2 from the numerator, what's that leave behind?
2,
-1.
Everyone plus or minus square root of 22.
Good, -1 plus or minus the square root of 2. Why did I factor out that 2? Why did I bother? Can't I just cancel the 2 into the 6 here? The answer is no. These terms are stuck together. You can't cancel into that. But if there's a multiplication here, now you can cancel. So now I can cancel out that, and I'm left with a 3 in the denominator. So it's -1 plus or minus the square root of 22 over 3. Whew. A lot going on there. Pause for you to catch up a second. Hannah, please.
Are you gonna put one of these questions that we just did on the exam? On the next
What's that?
You can use are you gonna put one of these problems on the exam where you have to use the?
I'll probably put several problems like this on the exam. Yeah. To give you more opportunity to get them right.
We'll have to get it wrong.
It's kind of like, it was funny, in England, they expanded the number of numbers that they had in their lottery. They went from like 40 something to 50 something. And they gave it the craziest spin. They're like, more numbers to pick from. And I'm like, well, wait a minute. Your odds have just gotten astronomically worse. So, I don't know, kind of funny. In any case, here's our roots. Now keep in mind that on WebAssign, you'll probably have to list them. So your roots are going to look kind of ugly. They're going to be, the first one was x equal -1, right? X was -1 was our first one. And then I've got x equals -1 plus the square root of 22 over 3. And then x equals -1 minus the square root of 22 over 3. Those are some pretty ugly roots, but those are our roots. That's what we're stuck with. Let's see here. Let's find out the factors that go with this. How about the first one? What's the first one?
x plus 1.
X plus 1. All right, so that's the easy one. So you guys missed a chance to do the easy one. All right, now it's somebody else for the next one. In the next one, you've got to move this to the other side, and it becomes kind of ugly. It's going to be x minus all of that. -1 plus the square root of 22 over 3.
Oh dear.
Yeah,
This is gonna be on the test?
repeatedly.
Oh gee. Oh.
And then x minus -1 minus the square root of 22 over 3. So for my YouTube audience, I was asked, is this going to be on the test? And the answer, well, let me soften the blow by telling you in Spanish. See. Yes, you will expect things like this on the test. Now there's one last thing we got to do, and that's put this together for our polynomial. So the polynomial is just going to be the product of these factors. So let me see if I can't squeeze it in here. So P of X can be written as X plus 1 times this term, which is going to be X minus -1 plus the square root of 22 over 3. And then X minus this one. Now, if you wanted, you could distribute that negative to both of those terms up here in the numerator, so it would look like this. X plus 1 plus the square root of 22 over 3. Maybe it's a little easier to work with it that way. So it'd be X plus 1 plus the square root of 22 over 3. And we're pretty much there. It's just one catch. If you multiply X times X times X, what would that give you? You multiply the first or leading terms. It's going to give you an X cubed.
How many times did you on the test?
What's the coefficient of our problem, though? What was the coefficient? The leading coefficient? It was a 3. We need a 3 out in front. I'm just going to put that 3 right here. If you actually looked at the graph of this polynomial and polynomial in D, they would be the same. So I'll let you finish copying that while I maybe plug that in, try and demonstrate that. So let me do this for a moment. Yes?
Why did you put the 3?
Because without it, when I multiply these leading terms, I get X times X times X, I get an X cubed. But the coefficient of X cubed in my polynomial was a 3. So I'm accounting for that little piece right there. So let me show you that these things give you the same thing. So I'm just going to type this in here.
Could you scroll down the page further? Okay.
Oh, no. I almost deleted this. There. Plus.
Do you know how many points this will be on the exam for this question? If you
How many
No,
times?
I don't.
How many times?
I haven't thought that far ahead yet.
How many times are we going to see this on a test?
Oh, there we go. Minus. Oh, plus there, and
this will probably be on the exam.
What's wrong with this? It's not. It worked out in my morning class. It's not working out now. I was bothered by this morning. There's something still bothering me about it now. Okay. What's wrong here? There minus that. 3. All right, there we go. All right, just to show you that these two things are the same, here's our first polynomial. So let me make that a little bit easier to see. Here's our second one. they're identical. So this is the correct factorization of this one. Messy, yeah, absolutely. But Hannah, in response to your question, I promise to put no more than 6 or 7 of these on the exam. All right, maybe a few less. Yes.
I have a question.
Yeah, please.
Exam.
What's that?
3.
Exam 2. Exam 2 is a week from today.
Okay, so it's gonna be on this exam.
Yeah. But I'll have a review for you guys that you can play around with.
It's not next week, the week
It's a
after.
week from today. Week from
No,
today.
it's next week.
Next week.
It's on Valentine's Day. It's my sweetheart gift to you guys. Yeah. In fact, here's another little sweetheart gift to you guys. In advance of Valentine's Day. Let's see. Let's do R equals
Wait, hold on a second.
4 times 1 plus sine of theta.
Oh my god.
Let's do. There we go. Isn't that special? Just for you guys. Yay! Happy Valentine's Day from a math nerd. All right. All right, so this is literally called a shape called a cardioid. Yeah, and for obvious reasons there.
Oh yeah, no, that's I'm right.
All right. Let's keep going. Let's see here. Let's do example E. Says find all the real zeros, use the quadratic formula if necessary. We're going to make example E a lot faster. Example E. We worked hard on the last one, wouldn't you agree?
Yes.
P of x equals x to the 5th minus 4x to the 4th minus x cubed plus 10x squared plus 2x minus 4. Wow. But there's something cool about example E that you should take note of. And that is example E comes along with a graph. So let's take advantage of that graph and some of the stuff we learned from section 3.3 and 3.2. So here's our graph. This is the graph of P of x from E. What do you see that's of note? What do you see that's worth noticing?
Oh.
The roots are next, 1 and 2.
Thank you. The roots are -1 and 2. All right, cool. So if the roots are -1 and 2, actually let me just kind of work things here. Roots, behavior, and then multiplicity. So I got roots at -1 and 2. All right, Caitlin's pretty down on this one. What's the behavior
The
of the root?
graph is not, for example, E.
Oh, it's not for example E? Or for example F?
I was like,
Oh, okay. All right, for example F then.
Okay.
Yeah, my bad. I was getting too excited. Yeah, we'll skip example A then. Sorry, we'll do example F. But what's the behavior though? And thank you for that, by the way. What's the behavior of the graph at -1? What are your choices?
Wiggle.
Yeah, bounce, wiggle, and straight through. And this one's a wiggle. Those are hugely scientific terms. Treat them with respect. How about at 2? What's the behavior at 2? It's a bounce. Now, what multiplicities go with each of these? What's the smallest one that I can get away with for a wiggle? 3. So let's get away with 3 for that one. The smallest one I can get away with for a bounce? 2. All right. So if x equals -1 as a root, then what's the corresponding factor?
X plus 1.
X plus 1. So that's going to be an x plus 1 cubed. How about somebody for the next term? Kyle.
Yeah.
How about for the next one?
X minus 2.
X minus 2 squared. And wow, I think we got this, right? We know all the roots. They're -1 and 2, and we've got this completely factored, right? Wow.
was easy.
Yeah, a lot better than the last one. Nice.
So these are the ones that are gonna be in the test, correct?
Yeah, there'll be ones like this on
How
the
many
test
times?
too. I'll keep them balanced,
How
all
many
right?
times?
And for Hannah's sake, we'll put at least 7 or 8 of these on the exam, right? Now there's a couple more down here that you could practice with yourself. Let's take kind of a quick look at this one. There's just basically one difference between this one and the last one. Does anyone know what it is?
It's a negative.
This has got a different end behavior, right?
Yes.
So this is going to be an odd degree because the tails point in opposite direction, but it's going to be a negative one. So this is really the negative of the first example F. So it's going to be P of X equals negative of X plus 1 cubed. That could, actually not quite. So that's going to be an X minus 1 here, right? Negative of X minus 1 cubed and X plus 2 squared. Because you get a wiggle at 1 and a bounce at negative 2. So let's just pretend this part never happened. There we go. Beautiful. So you should be able to reverse engineer some of these things. I'll leave you that one to practice at home. But, this all starts to dovetail into each other very nicely.
Let's get the negative in front of the negative.
Negative in front of this one?
Yeah.
So from the end behavior of polynomials, we know that because this goes up to the left and down to the right, that it has to have a negative leading coefficient. So I think I've got the handout from the other day over here someplace. Let's see. Bounce and wiggle. Yeah, where did it go? Where'd it go? Division. I'm not finding it at the moment, but it's from our end behavior of polynomials. Should be in one of these sections. Bounce and wiggle. No, that's not it. Page, no. Yeah, I'm sorry.
I understand.
Yeah, here it is. Here's our.
Yeah.
So it has to be something like this because of its shape. Has to be a odd degree, negative leading coefficient. If you take a look, what's the degree of our polynomial? If I multiplied it all out, what term would I have as a leading? Yeah, I'd have x to the 5th. I got 3 x's here. I got 2 more of them here. I'd have an x to the 5th. So that matches what we've got in our graph. Cool.